guess we should start, right?
Sure.
Okay. So it's my pleasure to introduce Alex Brodsky, who's going to be the speaker at our joint computer science at SCOR seminar. Alex is professor at computer science department, and he works on analyzing complex systems, which is a SCOR topic, and uses computer science tools to do that. So he's going to present on the overlap of those two today.
Okay. Thanks for doing. So, so thank you for coming. It's a pleasure, and I hope you'll enjoy and will learn something out of this presentation. So let me just acknowledge the sponsors over the years and PhD students. Right, all of the work I'm talking about is theirs. I'm just presenting. Well, probably I contribute a little bit. Okay, so what is the whole thing about? What are decision guidance systems and how they relate to decision support systems? So decision support systems is an extremely broad term used in so many different contexts. Anything that does something, right, with gathering data or helping in some way to making decisions, people call decision support systems. Decision guidance systems is a subclass of decision support systems geared to do two things. It's geared to elicit knowledge from domain experts, typically in the form of formal mathematical models, right, or proxy of these models, and provide actionable recommendation to human decision makers with the goal of arriving at the best possible course of action. So the fact that the system, possibly collaborating with humans, must provide an actionable recommendation of what they should specifically do. It's not just helping them or giving them information, giving some insight. It's saying, right, we need to converge to a decision that you can actually actuate. That's very important. And in a broader way, if you think about decision making, we have this dichotomy. We have on the one hand, much more operations research side. When you have lots of technology has been developed, mathematical and constrained programming and a variety of techniques, but they always assume that you need to have a fully formalized mathematical model. So this is one extreme of the spectrum. You can do a lot of things when you have a formal model. On the other hand, you have the other extreme, when you have human experts in a variety of areas that often make very smart decisions and very insightful decisions, but they cannot put it into a model or an algorithm. And in general, it's a fascinating area of how you can bridge the gap on get expertise from people on the one hand and formal mathematical techniques, right, to do better. So that's kind of the overarching things. So let me start with giving you a couple of examples to make our discussion a bit more concrete. So you have decision guidance in a variety of systems, complex systems. Supply chain, of course, is a very traditional system. And you have here both operational type of decisions as well as investment and planning decisions. And you need to construct models for supply chains, but also you need to perform various kind of analytics. You may want to understand what is going on in terms of what happens with inventories, with the status of our equipment, delivery, and so on and so forth. This is kind of descriptive analytics. We may be interested in diagnostic analytics, understand why something went wrong, why did something happen. Predictive analytics to understand if we run our system operationally or in terms of investment planning in a particular fashion, what we can expect to happen. And of course, the most important, the prescriptive part, optimization part, how do we set up things, right? All of the decision variables and controls as to move the system into the optimal point, optimal whatever that means in the context of decision makers. Okay, you have very interesting applications in the power space, and that's where we do a lot of work along with manufacturing. So this is a very interesting domain, particularly introduction of renewable energy. So for those who are not familiar with power systems, traditional power systems are top-down and centralized. You have a fossil-fired power plant generating power by burning fossil fuels, and you have the demand from either residential or commercial and industrial customers. In a traditional power system, everything is driven by demand prediction, which in turn is driven by weather forecast. And today people know to make very, very accurate predictions of the demand from the forecast, knowing the time of the day and so on and so forth. People make prediction of 8 hours ahead. And then people solve the so-called unit commitment problem, in which they decide in every market, right, every power station, and in fact every turbine, how much power it needs to generate, whether this power, how much of this power stays in the local market and distributed there, how much of this power is transmitted to other markets, right? And then goes right from the power generation to transmission and distribution to residential and commercial customers. When people introduce renewable energy, the system becoming order of magnitude more complex. Why is that? First of all, renewable sources of energy such as solar and wind may appear not upstream but downstream of the power system. They may be local, like on our campus, like in a microgrid. But the second most important thing is unpredictability of power supply from renewable sources. So the traditional power systems are the so-called dispatchable. You can tell a power plant, right, in 2 hours I want this power, and in 30 minutes I want this power. But you cannot tell it to a photovoltaic array, to a solar or to a turbine. If there is sun, it would produce. If there is no, and the same for the wind. And if you have a very small percentage of your portfolio from renewable sources, it does not matter too much. But if you have 50% of your portfolio, 40% or 60% of your portfolio from renewable sources, what may happen that you have a system that operates, and all of a sudden you have a sudden reduction of supply by a significant percentage. And then power systems must be balanced at all time, otherwise there is an outage. Otherwise there was a blackout. So you need to immediately decide how to redistribute supply and demand, right, through control systems. If you don't, system collapse. And how do you do it, right? You need to either reduce your demand, and some people are not happy when you do that, or you need to compensate by generating power. But if 50%, if your reduction in all of a sudden in 5 minutes, 20% or 30% of the power generation, you need a lot of capacity, and most of the traditional plants are not capable of ramping up so quickly. So the system is becoming much more complex and much more dynamic. And you need to make these decisions of redistribution of power every 30 or 15 minutes for a certain time horizon forward. And of course, one of the ideas to compensate this is to use some power storage. So you can have, and you have power storage like these batteries, lithium batteries that you can put downstream. These are very expensive batteries, like $1 million a piece. And they only, the lifespan is not too long. So it's very expensive proposition. People use flywheels for frequency regulation, so this kind of storage. Well, capacity is not great, but that they're very quick. And they have this hydro storage, in which, in lieu of the storing physically power, right, when you have extra power, you pump the water up to a reservoir, and then when you need it, right, you allow to regenerate it through the hydro turbines. So this is a very complex system, and again, in those systems, like in supply chain, you need to construct models which are very complex, and you need to make a range of analytics from descriptive, diagnostic, predictive, and prescriptive optimization to make actionable recommendations. Another very interesting domain in which we do a lot of work is the area of manufacturing. So this is an example of a Tesla production process, an actual process, in which they take aluminum coils, they uncoil. There's huge machines that uncoil these aluminum coils. They cut it into various pieces, like left side, underbody, front, right side. They put it into a deep press to make them form. Then it goes to the second phase of the body shop, when they do the so-called internal reinforcement and welding to make it more stronger, body assembly, washing, coating, and painting. And then you have some external components coming from OEMs, and they have a final assembly in a Tesla car coming out. So it looks simple on this diagram, but of course these processes are incredibly complex. Every machine has very complex physics-based models, right, controlling, right, their output from throughput and understanding the transformation of energies and power and so on and so forth. They're very complex physics-based models. You need to understand how you operate it, how do you do it operationally, and even more so, how do you do investment or planning of this. Okay, and again, you have from descriptive analytics, what's going on, to diagnostic, why did something happen, why did something go wrong, to predictive, what will happen if we operate it in a particular fashion, and how to set it in the optimal fashion. Okay, and to give you a little sense of how a decision guidance systems may look from the perspective of the users, domain-specific users. Okay, look at this example that we prototyped to build for the National Institute of Standards and Technology, which is designed for process engineers. And I'll exemplify it using the Tesla production process. So it's actually a system that can make them actionable recommendations. So here you don't see it, it's too small, but you have a hierarchy of various components and sub-processes in a more complex process. And then the user can drag, right, and drop on the palette and create a diagram representing the flow of the process. So this representation corresponds to the left part of my previous diagram. This is uncoiling, this is cutting, this is depress, right? And similarly, the user can do and represent, and every component, if you click on it, has a very particular data associated with it. And part of this data are fixed parameters of this equipment, and some of it are some control variables which may not be known. Okay, and so you can, in the system, you can click on various components and dive, zoom in, and see precisely either the setting or parameters of all of your systems. And the user can similarly have the second phase of the problem, which is the body shop, in which you have this internal reinforcement and welding and washing and body assembly and the rest and the final assembly. Okay, or the user can combine the whole thing. I say, here's my prep, here's my body assembly process, here are my work in process inventories. The process engineer, an end user, will show the flows, okay? And the system would interpret this composition as a formal mathematical model, right? So underneath this graphical composition that the process engineer does, system understands it in a very formal way. And then we can say, we can do various analysis with it. We can say, here is the overall Tesla process, and here is the process I want to do. I want to do, let's see, it's too small. I want to do a deterministic minimization. I want to find all of the control parameters, all the settings of the machine in the entire process, as to reach my demand at a minimal cost, as an example. Okay, and you'll press the run button, the process engineer, and what will come back is something that looks structurally exactly the way that it looked before, but now if the process engineer dives into individual components, it will find all of the control variables instantiated, which would do, okay? Underneath this process engineer, right, there's a system that I'll be talking about that trying to understand this high-level model and machine generate underlying mathematical programming model, in this case an EMPL, submitted to a mathematical programming solver, and in this case Cplex, right? Solve the problem, propagate things back, and present the results here. Okay, so that was to give you a sense how the systems may look from the perspective of the domain-specific users. Okay, so what is it I want to do in this presentation? So I want to talk to you more generally, what are the needs, challenges, and the vision for decision guidance systems. And then kind of mostly the work my team is doing in this area, you can split conceptually into three major areas. How do we develop languages and tools to make the development of the system much quicker? Okay. The second area is how to develop a variety of algorithms to support this process. The point is that because you keep the model components in the system, you can utilize various special properties and develop algorithms that utilize mathematical properties that online algorithms cannot. You can do better. Okay, and we work a lot in developing those algorithms. And the third is how to apply it to a variety of areas. And you saw a couple of examples. Power, manufacturing, we apply it in public policy, in renewable energy, and a number of areas. Okay, and my presentation, I'll exemplify this language in a tool called DGAL, Decision Guidance Analytic Language, and Unity Decision Guidance Management System. I'll give you a couple of examples of algorithms. One dealing with stochastic optimization, based on white box deterministic approximations, and another optimizing multi-stage production service network, which is a highly combinatorial and nonlinear problem through preprocessing and decomposition that are otherwise impossible. Okay, and I will not be talking too much about a specific application, but we do build a system for service networks for NIST, for the National Institute of Standards and Technology, which we put online. Okay, and then I'll give a few more broader words about kind of a broader view of the research, and would like to end with kind of opening 3 grand challenges. Right? What we can do with decision guidance if we combine it with Internet of Things protocols, right, to build smart cyber-physical systems. How we can do a smart design when you have a design, whether it is product design or process design or architectural design, various kinds of design, how you add decision guidance to it to make a much smarter parametric design and develop it quickly, and how to apply it to public policy. So I would like to leave you with those things. Okay, so let's start with the needs and challenges. So if you look at what typical decision guidance needs to do, there's a range of things that they need to do. They need to use and mine large amounts of data coming from a variety of sensors and a variety of sources. They need to elicit knowledge about model structure from domain experts. In examples I gave, it's physics-based equation, dealing with physical processes or engineering equipment, or financial models and so on. You need to elicit deterministic or stochastic, to learn deterministic and stochastic models. Many of those models that you elicit from experts are parameterized, so you need to train those models from the data, in historical data. You need to understand what the user, what the decision makers want, eliciting metrics, key performance indicators, and decision objectives. And it is more complex when you have a group of decision makers. You want perform then a variety of analytical tasks I talked about, right, from monitoring, the descriptive part, diagnostic, prediction, optimization for prescriptive part. You would like to explain actionable recommendation to decision makers, why you're recommending certain things. You want to solicit their feedback for iterative improvement. So this is the range of things. And let us understand how the systems are being developed today. Okay. So typically, you have some end users, which are not operations researchers, which are not computer scientists, which are not data scientists. Some of them are completely non-technical, some of them technical in their area. For example, a process or industrial engineer, they may be pretty technical, but not in operations research necessarily, or not necessarily in computer science or algorithms or modeling. And they would like to perform a variety of tasks that will help them to make decisions. Nobody implements this functionality from scratch, so there is a lot of powerful technologies, of course, that they want to use, or obviously mathematical constraint programming. So you have very powerful solvers that people in operations research domain, mathematical programmers, spent over last half century developing extremely efficient algorithm for various classes of problems. You have a lot of simulation technology, so not all things can be just expressed in analytically closed form. Some of them are simulation. There is a lot of research on simulation-based optimization, but compared to what you can achieve by mathematical or constraint programming for models that are describable in closed form, typically you can get much better results in terms of efficiency and optimality in using mathematical programming as compared to simulation-based approaches. But lots of people work for more complex problems than simulation-based. Obviously, you have a lot of work on statistical learning and data mining, and of course, a lot of database technology. So people want to use these technologies. The problem, however, that the underlying models, every one of those technologies requires completely different levels of abstraction and languages describing this abstraction. And often people modeling things ending up modeling the same knowledge, right? Whether it is equations for a physical piece of equipment or a network, they remodel it multiple times. Why? The same knowledge, because there are different tools that understand different levels of abstraction, right? So this is a complete waste, as opposed to modeling it once, right, and automatically generating specific models. And this results in a problem, so that when you implement the systems, typically the systems are one-off, they are developed from scratch, very difficult to reuse the systems, they are non-modular. To build them requires a lot of expertise, right, from a variety of diverse areas, from mathematics, operations research, IT, and so on and so forth. They are resulting in high cost, long development cycle, and once you are done, very difficult to modify and extend. So if you look at the models generated using traditional models, not trivial models, but really complex industrial models, they may span over pages and pages and pages of equations. And if somebody asks you, what would it take to only introduce additional feature of my system? It's a very complex proposition, because you need to understand have a very good grasp of how it will affect everything else. It's a very complex proposition. So this is very different from how people develop things in software engineering today. Okay? So we have a problem. We need a paradigm shift. And the key idea of the paradigm shift, right, you need to understand the analogy to database management systems. So database management systems today, like Oracle or SQL Server, are extremely powerful productivity tool. Nobody today develops information systems from scratch using an operating system and a programming language. Nobody. People use extremely powerful productivity tool, and it takes tiny fraction of the time to develop those systems. Okay? However, 40 years ago, people developed it from scratch. So in decision guidance, right, we are in the situation where database applications and information systems were 40 years ago, before the development of database management system. Of course, decision guidance systems are order of magnitude more complex. They don't just deal with manipulation of data, right, and various things. They deal with modeling, right, models, optimization, a lot of complex stuff, right? But the question is whether we can do a similar paradigm, okay? And that's exactly the idea. The idea is to make a paradigm shift and to move into what we call decision guidance management system, which is centered around this repository of reusable, extensible, and modular kind of knowledge base of analytic models. Okay, so the key idea is not develop this functionality directly from those tools, but rather to have this intermediate layer. And at the center of this layer, you have this repository of models, and I'll talk about these models in a second, right? And we'll call them analytic models. So I'll describe the analytic models in a moment in much more detail, but at a high level, what is an analytic model? Analytic model is not an optimization model, it's not a simulation model, it's not a machine learning model, it's a piece of mathematical knowledge. What does this knowledge describe? And it's written in some language, high-level language. What does it describe? It describes, if you have some process, it describes the metrics of interest of this process: cost, time, reliability, risk, right, and carbon emissions, and feasibility constraints, whether they are satisfied or not, as a function of fixed and control parameters. So that's what the analytic model does. And it is done in a universal fashion. Okay? That's some of these models, we call them atomic because they're described in language directly, and some of them are composite because they can be composed through an end user in some graphical or simple form. But either way, right, regardless of how they are composed, they are all having a formal description of how you express metrics of interest and your feasibility constraint as a function of fixed and control parameters. Okay, that's the key idea. Now, so if I have an analytic model, okay, and now I want to perform certain function against it. So if I want to perform a prediction, I can look at, if this model is stochastic, I want to do a prediction, I can do a variety of Monte Carlo techniques and predict it. Let's suppose I want to do optimization against this model. So, and I want to use mathematical programming for that purpose. So this is a model described in some high-level language. And I have not shown examples yet, which I'll do in a moment. But if you think conceptually about how this model is described, it looks like a simulation, a deterministic or stochastic simulation. And the model may be simple or may be extremely complex, corresponding to a huge code base. Okay, that's how it looks. Now, somebody gives you the only thing is this model is described using closed form computation.
Is the model necessarily differentiable?
Not necessarily, but you assume here, right, for the processes that they have some closed form. So you can put it in EMPL, for example, and submit to a solver. We're working on adding the black box as well, but currently the assumption is...
Which means you can differentiate it, right?
Right, and in most cases you can differentiate or you can approximate, right, differentiation in using various Newtonian Lagrangian methods. Okay, so if you want to perform now optimization against an analytic model, namely how do you instantiate the controls of the model as to minimize or maximize one of the metrics subject to feasibility constraints. If you want to use mathematical programming, a traditional way is you say, this is your model, use it as a spec. Now go back to your drawing board, use EMPL or PL or whatever your preferable optimization modeling language, and describe this model. And for simple models, it's not a problem. For models which are really complex industrial models, it's a very complex proposition. Instead, the idea of decision guidance management system is not to do it manually, not to hire an operations researcher to do it manually for a particular analytic model, but to machine generate an underlying mathematical programming model, for example, in AMPLE, right? And so this is machine generated. It is submitted to a selected solver, such as Cplex or Minus or SNOPT, whatever appropriate. Solver would solve it for you, will propagate result back, and will instantiate the results. Okay. So the idea is that you have universally modeled components that you can reuse and describe your knowledge about your system, components, physics, a lot of different things. And this description is very similar to how you would do it in an object-oriented code. Right? You have modularity, you can have libraries, you can, it's all reusable, right? But when you want to do some specific functionality, right, the system will machine generate an underlying lower-level model, such as AMPLE, okay, in order to use the best-known algorithms for that purpose, okay? That's the key idea. And this is done for every one of the functionality, whether you want to do learning or optimization and the rest, okay? So this was at a high level. Now let's consider this in a bit more, right. And an example, so for example, for National Institute of Standards and Technology, they ask us to develop this repository of models for the so-called unit manufacturing processes. So there's huge taxonomy of manufacturing processes, right? From additive manufacturing, casting, and forming, and joining, and machining, and molding, and drilling, and turning, a bunch of manufacturing models organized in a taxonomy. You can have, each one of them have various controls, right? Various velocities, various currents, and so on and so forth. They result in different outcomes in terms of the cycle time, the cost of the production, how much energy they consume, how much carbon emissions they generate, and so on and so forth. So they wanted to generate this taxonomy of models and be able to compose an arbitrary manufacturing processes using these components and be able to do analytics with it. So you can put in atomic models as an example, all of these models for manufacturing processes, which are basically physics-based, and you can put a higher level composite models describing your manufacturing cell or production line or a factory or a larger supply chain, okay? Or a larger concept of a service network. Okay. So let's see how these things work in a bit more detail. It was still kind of very high level. So one of the questions is just a background, particularly people who are not coming from CS. The question is, what language should we use in order to describe those models? So in the system called DGAL, Decision Guidance Analytics Language, and Decision Guidance Management System, we select a language, a database query language, or data manipulation language, called JSONic, that works over a data structure called JSON. So just as a background, I think everybody familiar with the relational data, when the data is organized in tables, and you have query languages, data manipulation languages such as SQL. Okay, they're very easy, but they're not sufficiently flexible for our purpose. The model is not sufficiently flexible, nor the language. But then you have semi-structured data using XML or JSON standards. Both are very, very easy. I can teach you JSON, for those who are not familiar, in literally 90 seconds. It's trivial. It's a hierarchical organization of data, and I'll show examples in a moment. And you can describe your data for whatever using this model, and then you have a query language doing the process. These query languages are not just query languages, they are powerful languages in which you can express mathematical computation in a very natural way. You can describe summations, equations, you can describe first-order logic in a very natural way, and so on and so forth. So they're very powerful languages, and they give you tremendous flexibility, right? Akin the flexibility of a programming language, yet it leaves you at a relatively high level of abstractions. So this is a choice. We could have used a different language. So that's what we will be using in the examples. Okay. So let me exemplify how this analytic model looked like. So conceptually, as I mentioned, analytic model is a piece of code, a function, described in a language, which computes some metrics of interest, cost, cycle time, carbon emissions, and constraints, feasibility constraints, whether they are true or false, satisfied or not, as a function of fixed and control parameters. So let's take a toy example to understand it. So let's suppose I have a trivial procurement problem. Okay? So this is a piece of data described in JSON actually, describing my procurement situation. I have some demand of 16 chairs and 4 tables, and I have some purchase info. I have price per unit, okay, so for chair by supplier 1, $50, and $60 for chair by supplier 2, and so on and so forth. And you have some availability information, right? Supplier 1 has 15 chairs and 3 tables and so on. And you have here quantities that you decide to purchase. Okay, I decided to purchase 10 chairs from supplier 1 and 2 tables from supplier 1 and 20 chairs from supplier 2 and 2 tables. Okay, so think of it as an input to the analytic model. So intuitively, right, if we wanted to make a decision of what to purchase, these quantity numbers would become our controls, our control parameters, because we decided of how much we purchase from whom in this toy example. And the rest of the information, such as price per unit, availability, we don't control that. This is fixed parameters in this toy example. Okay. And given that, right, we may be interested in computing what will be the total cost of procurement. So here we have just one metric cost, but we would have added other metrics. And we can have some constraints that we say whether they are satisfied or not. And in this context of procurement, we have 2 trivial constraints. One is you cannot purchase of something more than is available. So if I purchase 10 shares from supplier 1, I must have enough available. And I need to satisfy my demand in this toy example. So if I buy the total number from all suppliers as 30 shares, it must be at least the demand. Okay? So what is an analytic model? Analytic model is a function, which I'll show in a second, that takes this as input and computes this as output. Okay? And actually, that's how it is written in GSonic. Okay, I just extract from this input, procurement input. This is what you saw on the left. I just extract the structures. I compute the cost. This is the cost computation, right? Summation for over suppliers, over items they supply, multiply price per unit by quantity, I get the summation. I have the availability constraint for every supplier and for every item. Quantity I purchase of this item from this supplier must be less than available. Okay, and I compute for every item the total supply from all suppliers, and I say demand satisfied. So every item across all items satisfy the property that the demand is less than or equal to the demand supply, and I just return the structure that you saw on the right, giving the cost and procurement. So it's a toy example. Now, so having this analytic model, the question, how do we do optimization? So let's suppose, right, here that I don't know the quantities, and therefore I don't know the cost. And let's suppose that analytic model does a forward computation. If I know everything, what will be the metrics and constraints? Let's suppose we now have a reverse problem, which is how do I instantiate these parameters in such a way that if I run it through the analytic model, my constraints will be true, will be satisfied, and in such a way that among all feasible instantiations, my cost will be minimal. Okay, so you see obviously that this is an optimization problem, trivial in this case. In this case, I can do it manually, but imagine you can have a model which is extremely complex. So this is a minimization problem. So the question, how do you do that? So if you have this again in a traditional way, you have and you use to mathematical programming. You say it's nice that you have it written in some language. Now let's develop an ample model. For this particular example, it's of course a toy example. It's nothing ample or whatever language, but when you have a model which is a huge code base, right, developing this underlying model manually is a huge task. Okay, so that's what will be traditionally done. What do you do in DGAL and DGMS? You press the run button. You have the minimize function. Okay, what are the inputs provided to the minimize function? You take the analytic model, which is a piece of code, a function, written in language as input. So this function gets as input not just data, it gets the very same analytic model, piece of code. You give the same input as you've given to the analytic model, with the exception that your control variables are now to annotate it to say these are my decision variables of a particular kind. These are integers, these are reals, right? These are binary, and so on and so forth. And you say, this is my objective. So one of the metrics computed by the model, in my toy example, was just cost, but you may have multiple metrics, serve as my objective. And what is the output from this minimize function? The output from this minimize function is this input where all of the control variables, control parameters, are instantiated with the appropriate types, integers, reals, and so on, in such a way that if I would run right? So that's the instantiation that returned as output. And if I took this output and put it as an input to the analytic model, it will give me the constraints that must be true, of course, if the entire model is feasible, and it will give you the metric of interest selected to be minimal among all feasible instantiations. So what happens under the hood, right? So this model, right, analytic model, plus these inputs are going through very complex processing, right? Then the formal optimization model is machine generated. It is submitted to a solver, such as Cplex, such as MLP, or another solver. The solver solves the problem, propagates the result back, and we construct the results. So similarly, if you have any questions, don't hesitate to stop me, okay? Okay, now when we do that, so it's easier, of course, said than done, this process. And this process, reduction, so this is done through reduction. So if Q is our analytic model, the query, and D is the piece of input data, right, the semantics, right, is all feasible instantiations that minimize or maximize my objective. These are all possible answers that the optimal solution must give, and I'm interested in one of them. So this is a set of possible optimal instantiations. To implement it, as I mentioned, we reduce it to a more traditional mathematical programming problem, right, having equations like an ample. And some symbolic output structure that we need to remember. We apply the optimization solver, we get the optimal instantiation from the solver, we instantiate in the symbolic structure, and we populate the result. So what should be the connection between these two sets, the semantics and what they produce? Okay, they must be equal, right, ideally. So we would like to have these two properties, otherwise our reduction doesn't work. And these properties must be formally proven, otherwise you're not sure whether the system does the right job. So one property is the soundness, saying that any answer that you generate through this reduction process is a subset of what is allowed according to the semantics. Namely, if your reduction and solving, right, produce the result, it indeed must be an optimal, right, feasible, optimal solution if it is feasible. And you may want to have the other way around. Every possible solution can be generated here. This, you always need soundness. Completeness, you can be relaxed. You can just say that if the original problem is feasible, then you must generate a feasible, right, an optimal feasible solution. Okay? So similarly, you do it for other functions, such as the learn, right, training function. So in the training function, you provide analytic model. You provide the input when temp parameters are not known. You provide a training set, which is a set of input-output pairs of the model. Okay? So what does this function do? It optimally instantiates the parameters. How does it do it? Okay? It constructs the arrow function. It constructs an optimization problem that minimizes the arrow function. It solves it, right? It populates the results. So it's a regression. It's not a linear regression, of course. It's a regression of the function which is implicitly described through the analytic model. Okay? And this is done again. The model are machine generated and solved using underlying solvers. So models can be, the example I've shown show the deterministic models. But the models can also be stochastic. So what is a stochastic model? If I do the same computation as I've shown you before, but I can add some noise. For example, my price per unit, right? What if PPU is my expectation, but I may have some stochastic noise, because it will be in the future, there may be some fluctuation of the price per unit. So essentially, you can have the same model, plus you have primitives drawing from some probability distributions, or the demand. This is the expectation of the demand, but the actual demand may change, right? And you draw from some random distribution, and you say, here is the expectation of this noise, which is 0, and the standard deviation of this noise is 2% of my demand, of my expectation, and so on. And for these stochastic models, you can do predictions, and predictions are similar to the original analytic model, except they return now not the number for these things, true, right, for arithmetic values, and not necessarily true or false for the Boolean values, but they now result some characterization of their distribution, mean and the standard deviation. And for constraints now, the constraints are not just true or false, they are true now with certain probability. So this probability is the answer. Okay? So to summarize this DGAL, right, it's a language based on a knowledge base of analytic performance model. They express constraints and metric of interest as a function of fixed and control parameters. Critical is that they are independent of specific analytical tools and algorithms that you are going to use. And that's very important. It allows you to manage this knowledge base. They allow a variety of analytic functions, right? Optimization is the key among them. It performs operations by automatic reduction, and it uses the same language for both invoke these operators and integrate them into larger workflows, and the same language is used to describe the models themselves. So it's different from taking, for example, a Java library allowing to, let's say, the concept interface, IBM, allowing to encode in Java an optimization model, right? So you describe the model through a certain library, right? Not in the same language, okay? As opposed to describing them in the same language. Okay, so that's much easier.
So the stochastic the additive term, stochastic additive term, only used for predictions, not for optimization, right?
For optimization as well.
So
what we support is, right now we support one stage optimization, and in fact I'll be talking about it in a moment. Okay, now because we don't have too much time, let me skip more details about the decision guidance management system and how it is implemented. But the key idea behind the implementation of this is symbolic computation. So when you have a code that looks like simulation code, the question is how do you do symbolic analysis of the code and how do you generate underlying low-level models, okay? And there are a lot of techniques of symbolic computation, which I'll skip for now, okay? And when we do experimental study and see how much penalty may pay by machine-generating models, operations researchers, when they generate models, they may use a variety of tricks, right? So there are small changes in the model that may lead to significant changes in performance, and these models are machine generated. So machine probably would perform not as well as an expert operations researcher. But in the study for combinatorial optimization we used, the reduction looks pretty much linear, right? So you pay some linear penalty, and it doesn't deteriorate. But so these are preliminary results. Of course, I'm sure we can find examples when, for some particular problem, right, a smart trick by an operations researcher can do better. Okay, so let me exemplify algorithms, and probably I will not have time to talk about both, but let me talk about the stochastic optimization based on deterministic approximations. Something that would allow us to integrate with Unity and utilize the structure of the Unity DGMS. So the problem is a one-stage stochastic optimization, which I've formalized at the moment, over closed-form arithmetic simulation, which I'll define in a moment. And the solution is this GSODA algorithm, okay, which is stochastic optimization based on deterministic approximation and experimental results. So let me say a little bit how this works. So first of all, what do I mean by a stochastic closed-form arithmetic simulation? So it's a sequence of computational steps, right? Y1 equals to some expression, Y2 up to Yn, where every expression, right, is either arithmetic or Boolean expression. And this expression is allowed to use the input to the simulation, which is a vector x, or previously computed y's. Okay, so this is kind of a trivial form. Of course, you can think about that very complex simulation can be viewed as in this form. Okay, and so some of these left-hand sides are stochastic and some deterministic. So if the expression here, so these expressions can be either a Boolean or arithmetic expression, or they may invoke drawing from a probability distribution. So when a particular y is stochastic, when it is either draws from a probability distribution, that is stochastic, or recursively, right, if its expression uses another variable which is stochastic, okay? And all the rest are deterministic. Okay, so what is the problem? The problem looks like this. There's some cost function, whatever that is, over the input x, and I'd like to minimize the expectation of that. And we have some deterministic constraints, and we have some stochastic constraints. So stochastic constraints, we have some stochastic metrics, which must appear on the left of the sequence computation. And this metrics must be above some bound with certain probability. Right? This is the stochastic constraint. Okay? So this is a problem. Now, how is everything is described? How this cost function is described, how these constraints are described, how these metrics are described. they are described through the simulation that I've shown you before. So all of these things, C, cost, MIs, must appear on the left-hand side of the simulation. Okay? MIs are stochastic, C is a Boolean value which is deterministic, cost is a possibly stochastic value. Okay, so how people generally work on stochastic optimization? So at a high level, there are two major approaches to solve stochastic optimization problems. One is simulation-based approaches. So you have algorithms that use simulation as a black box. So you have a variety of genetic algorithms, a variety of local search algorithms, which are based on a simulation black box component. Okay, and these algorithms, if simulation is a truly black box, you have nothing to do, that's what you have at your disposal. Unfortunately, this method do not utilize a mathematical structure of the underlying problem, if possible, and therefore they are not very competitive against mathematical programming for deterministic parts. Okay? Some, of course, techniques are more sophisticated. They still treat the simulation as a black box. However, they're trying to construct a surrogate model as they go along, like Bayesian optimization. So you try to sample your space, and when you sample your space, you try to construct some mathematical structure, right, of your exploration, to construct a surrogate model to help you out. But still, in order to construct it, you need to spend all of this very expensive steps of sampling your space. Okay? So GSODA takes a completely different one. It leverages the fact that the model we have is closed arithmetic form, and instead of trying to extract the surrogate model, right, it does symbolic analysis of the simulation program, and machine generates a deterministic approximation, a surrogate model. Right. So this by itself is not a trivial proposition how to generate the surrogate model by analysis, and that's where Unity DGMS comes very handy, right? We use Unity DGMS to do symbolic analysis and generate the surrogate models. Let's understand that in a bit more. So if this is the original problem that I've shown you, we want to have a deterministic approximation in which all of the components are deterministic now. So we have some cost zero function instead of this stochastic cost. C was deterministic to begin with. And this matrix, right, we would like to have the deterministic approximation. So the question is how to do that in a smart way. So first of all, when you look at the simulation program, right, even if we have symbolic analysis, so one idea, simple idea, every time we draw from a probability distribution, what if we replace the random value coming with their expectation? Okay. So if you do that, unfortunately, and solve the deterministic problem like this, then the original stochastic optimization problem is not likely to satisfy their stochastic constraints with the acquired probability. So the next idea may be, what if we have some conservative adjustment, right, when we draw from probability distribution? What if we don't like expectation, but take more or less? In order to use this idea, right, first of all, you need to understand how taking more or less than expectation, how would affect the satisfaction of stochastic constraints, whether it will increase the probability or decrease. And in some cases, it's impossible because the function may not be monotonic, right? So doing this conservative approximations inside the simulation program is very complex, okay? So what the trick here is different. And if you look at the bounds here, right, what GSODA does, it does take just regular expectations from the simulation. However, these bounds that are used here, right, are conservatively approximated. So you artificially increase your bounds that you must satisfy, so that even if deterministic optimization, right, gives, right, satisfies with this increased bounds, then when you go to the original problem, when the bounds are less strict, hopefully the probability will be sufficiently high, right? That's the idea. And that's exactly the idea of this algorithm GSODA. And at a high level, it has these two main phases. One is how to generate. So the original problem, if you discretize your controls, it's a huge exponential space, right? So the question is how to generate a very small number of candidates which are near optimal, right, or very promising. And once you have a small number of candidates, you can refine them using more traditional simulation optimization techniques. And the techniques we're using is OCBA, Optimal Computational Budget Allocation, that Professor Chen, who is teaching a class now, right, kind of a founder of this techniques. Okay. But the question is, so this is a more traditional one using OCBA So every iteration, you allocate budget for various simulation runs that maximize the probability of coming with a true optimal answer that you cannot beat. I will not be talking how this works, but we use existing techniques. The question is how to get this small number of alternatives. Small number, maybe a few hundred or a few thousand, which is nothing compared to the original discretized space. And the idea is that there is an inflation phase and there's deflation phase. In the inflation phase, these bounds that I've shown before are escalated, okay, in a very aggressive fashion so that hopefully we can come to a feasible solution to the stochastic problem very quickly, okay? And they use statistical approximations using some simplifying assumptions as a heuristic to get to a feasible solution very quickly, because we would like to generate a feasible solution very quickly. And then, because in this aggressive process of inflation, we can overshoot what we need. And deflation kind of takes this bound much more gradually down, right, to refine it. That's the key idea, okay? I probably don't have time to talk about these phases in detail. I can point to your papers, but I think you got the basic idea. I don't have time to talk about the other algorithm, okay? And it turns out, so we did experimentation with this problem on the problem of service networks, which are combinatorial problems. They have stochastic constraints. They have manufacturing processes, which is physically based. You have elements of a more traditional supply chain, but most of the constraints here are nonlinear physics-based equations, right, for transformation of power and stuff like that. And the point is that the result is just order of magnitude. So this is GSODA, which utilizes the symbolic preprocessing. This is simulation-based algorithms. So we used 4 from a package called JMetal. So Mohan, who graduated last summer, he took the best 4, he experimented with many algorithms in this package, took 4 the best algorithms from it compared to GSODA. So this is a logarithmic space of time. What's interesting that GSODA finds a feasible solution very quickly, not particularly good one, but very quickly, like literally in seconds. And then, right, it slowly gets to almost the best it can reach within a day, right, and slowly improves. Simulation-based algorithm, it takes hours to get the first feasible solution, which is not good. After a day of running, there's still a gap of 42 or 48% in terms of optimality. And if you run it for 3 days, it's a similar situation, right? It takes much longer for the simulation-based algorithm to reach that, whereas GSODA, and still after 3 days of running, there's still a 25% gap. So the difference is very significant. It doesn't mean that simulation-based algorithms are not good. It just means that GSODA utilizes some structures that they do not utilize, right? Through symbolic analysis, and by using the property, right, by extracting mathematical structure directly rather than learning it. Okay. So I'll skip the other example of the algorithm dealing with combinatorial optimization and decomposition, and just give a little bit broader view on the decision guidance research. There's some delay, funny. Right. So I mentioned that the work works on languages, on algorithms and system and applications, and you have work on combinatorial optimization using the fact that you can pre-process much of the model stored in the repository, stochastic optimization, regression algorithm for piecewise linear functions that correspond to the structures in the language, classification of a multiple sequence, and a range of things that my students have been working on. For languages, the key idea is people who use these techniques, right, you cannot push them and teach them to be operations researchers. So you need to bring the abstraction to their skill. If you're a Java programmer, you want to bring them something that looks natural in Java. If you're a database programmer, a query language may be appropriate. If you are a process engineer, right, you may want to use and integrate it with a CAD tool. So that's kind of the key idea. Okay, so let me say a couple of words about the challenges that I want to leave you. So one question is, right, what is the connection between IoT, Internet of Things, right, and the creation of cyber and physical systems? So this is kind of a very rhetorical question. The answer is decision guidance. But here is the key idea, right? If you look at the IoT, you have a number of phases of the Internet. So what is the purpose of IoT? You have complex cyber-physical systems out there. The question is, how do you integrate cyber-physical systems? So integration of cyber-physical systems into a more complex system is a very complex proposition. IoT created protocols in which you can wrap them into a protocol allowing to get a state of some, right, external service, not computational service, cyber-physical service, and actuate controls. So integration of the systems is becoming much easier, okay, using IoT. But the question is, how do you make sense out of it? So if you look at how cyber-physical systems look like, you have the execution system, and you have, in a cyber-physical system, you have the atomic components, whether it is in smart home or connected cars or industrial processes or supply chain. And you have the composite cyber-physical systems, which try to achieve some higher level result from the components. But the question is, how do you decide of how you actuate your system? How do you decide what is happening? How do you decide what is going to happen? So the typical approach today is to create the so-called digital twin. You have a physical system, you create a digital twin which model, right, model mathematically everything, and then once you have the models, you have a bunch of tools and algorithms at your disposal. Unfortunately, this proposition of modeling everything for every combination of your system is just not scalable. It's just not practical, okay? And the key idea is using this decision guidance. And the idea is when you develop atomic components, you associate this analytic performance model with it. And for the composite structures, you develop this recursive composite models, like the service network that I didn't talk about much. And every time you compose your system into a ledger, you automatically have the underlying digital twin in the form of analytic model. And then if you use Unity DGMS, you can do all of these good things, right? From descriptive to predictive, diagnostic, and prescriptive optimization analytics, okay? That's the key idea. And you have a similar idea when you think about design. So imagine you design a product using a CAD system, computer-aided design. So you have an expert designer who goes through various steps. I decide on the geometry of the product, how various parts of the product, physical product, are connected, material I'm going to use, and so on and so forth. And after working for half a day, all of a sudden he decides that she decides they want to change something. Okay, back to square one. Okay, so that's very complex. Instead, the idea is to have parametric designs and to associate analytic model on top of the parametric design, so that when the designer does it, it doesn't say my geometry is this very specific numbers, but rather it is x by y and by z. Okay, but you put constraints and limitations, right, in terms of the analytic model. You put, okay, and then once your design is not a one design, right, you get a parametric design, and you have analytic model on top of that, and it defines effectively a family of specific designs which make the underlying analytic model be feasible. Okay, and then you can your actual design may be the result of optimization or trade-off analysis. A lot of good things you can do rather than doing one design. So this is kind of a very promising thing. You can do it at different levels of design. When you design a product, or when you design a process to execute it, when you do architectural design. And similarly, when you think about instrument of public policy, investment of public policy instruments. Okay, I'll stop here. Right, so that's the main goal of building a robust decision guidance management system, and okay, and hopefully it can make a significant impact. Okay, I'll stop here and take any questions.
Just maybe have time for one quick question, because we're out of time for that.
So you spoke a bit about the reduction. You skipped some of the points. I think you actually didn't go over exactly how the reduction is being done. Mm-hmm. Does your reduction model actually accommodate for any combination of the constraints and everything, or do you have predefined set of domains which you actually?
It's not predefined domains. It can reduce an arbitrary closed form simulation program written in this language, JSONic. Right. You can have an arbitrary simulation program, and we have a provingly correct reduction. Yeah, the key idea behind the reduction is to take your original code and overload arithmetic and Boolean operators with their symbolic counterparts. That's the key idea. I can talk offline if people are interested.
Let's thank the speaker again.